Okay, the remainder of section 3. Top of the next page, it says friction. Friction forces are actually due to a couple of different factors. One of them is roughness. If I my box of gloves here again. That's below the camera. Okay. 2 boxes of gloves. 1 is good, 2 must be twice as good. So if I want to push the 1 box across the other, well, these surfaces look pretty smooth to the eye, but if you put them under an electron microscope or something like that, it'd be mountain ranges. And as you try to slide the one surface across the other, the snags get caught on each other. So that's part of what's going on, but it's not the whole thing. Because if friction was just entirely due to roughness, it would follow that if you made surfaces extremely smooth, they would get extremely slippery. And actually, the truth is exactly the opposite. If you have something like a steel plate and you try to slide a steel block across that, and if you polish them right up so they're just like mirrors, what you'll find is that actually it gets extremely sticky rather than sliding very freely. The reason for that is that what holds each object together in a rigid structure is bonds, chemical bonds that form between the atoms. Like if each one is a piece of steel, most of the atoms are iron, or a lot of them are at least. And so here you've got an iron atom, here you've got another iron atom, you get them close enough together and they start sharing electrons. In the case of a metal, the electrons are shared in such a way that the electrons don't quite remember which atom they came from in the first place, which makes them pretty much free to move throughout the whole piece of metal, which is what makes them good conductors of electricity, but that's a story for another day. Point is, you get 2 atoms close together and they start sharing electrons. And this is true even if it's one of the atoms on the top of this surface and one of the atoms on the bottom of this surface. They're just a couple of dumb atoms. They don't know they're supposed to be part of different objects. If you put them close enough together, they form a little bond. So on a really smooth surface, a lot of the atoms will be in close proximity to atoms on the other side of the surface, and you get what amount to a lot of microscopic spot welds forming everywhere. And that makes the 2 objects adhere to each other also. So that is sort of the nature of friction. But as far as how does it behave, let's consider what if you have one object that you're going to slide across another, and starting with a force of 0, you push on it harder and harder. And well, in this case, I don't have to push very hard to make it start to slide. But if it was, a 200-pound wooden crate you were trying to slide across the floor, that would, you'd have to kind of exert yourself. So we can divide it into 2 cases, static and kinetic. Static friction is when the objects remain at rest, so there is no slippage across the surfaces, okay? And so in the static case, you've got a block you're trying to push across a table or something like that. This is you pushing on it. Down here along the surface, there's the force of friction, pushing back the other way. And of course, there's also a couple of vertical forces. There's W for weight, gravitational attraction to the Earth, and then the supporting force that comes from the table it's sitting on. I'm going to name that with a lowercase n. Now, in the static case, as long as it's an object at rest remaining at rest, the sum of the forces have to equal 0. An imbalance of force causes acceleration. If it's going to just sit there all day, the friction force has to be equal in magnitude, opposite in direction, but equal in magnitude to how hard you're pushing, because the forces have to balance if it's going to sit there. Okay, so you start out with 0, friction pushes back with 0. You go up to 1 Newton, friction pushes back with 1 Newton. 2 newtons push, 2 newtons friction, and so on and so on and so on, up until there is some threshold. Sooner or later, no matter how sticky these surfaces are, you'll break them free. Even if you've super glued something to the floor, if you back up the bulldozer and hook up the chains, you'll be able to tear it off. So eventually you reach the point where friction just can't hold it back anymore, and your pushing force wins. This maximum friction force, that if you push any harder, it begins to move. I'm going to call it Fs for static friction. The maximum friction force basically depends on 2 things. First of all, well, let's start with this. N stands for normal force. That's how hard the 2 surfaces are being pushed into each other. Okay? If I want to, well, it's below the camera, but I've got my green box full of gloves here. If I want to drag that across the table, I don't have to pull very hard at all. That's a force of just a few ounces. If somebody came and stood on top of it, I would have to pull much, much harder to make it start to slide. Now, it's still the same materials. It's still the same box sliding across the same table, but you press them into each other harder, and that makes the friction force, the maximum friction force, bigger. Okay? And that force that describes how hard they're being pushed together, that's this normal force. The other factor is what materials are involved. I mean, everybody knows that if you're walking on ice, you're more likely to slip and fall on your face than if you're walking on dry pavement. The slipperiness or stickiness of the surfaces is rated with this number called the coefficient of friction. Okay? For dry pavement, the coefficient of friction would be relatively large, probably around 1 somewhere. If you're walking on ice, especially if there's, if it's a warm day where there's a little bit of water on the ice to act as a lubricant, this would be 1 or 2 tenths. Okay, so big number means sticky, small number means slippery. Now, if you do push hard enough to get the thing moving, then you're dealing with sliding friction rather than static friction. But if I called it sliding friction, I'd have S for static and S for sliding, and that would make the whole subscript thing pretty useless. So we'll call it kinetic friction instead. Same idea. How large the friction force is depends on how hard you're pushing the two objects into each other, and it depends on the materials and the condition of the surface. And one other thing maybe I should mention along with this is that usually kinetic friction is weaker than static friction. The surfaces can't get as good a grip on each other when they're sliding across each other as they do if you let things settle in. So usually in my mind, the classic example of this sort of thing, of course, as happens a lot in an introductory course like this, I'm oversimplifying the situation, but you're trying to get a spark plug. You're trying to change your spark plugs. Okay, those spark plugs have been in there 50,000 miles. It's time to put in some new ones. And you know, spark plugs are cheap. They're just $1 or $2. Well, if you get the fancy ones, they're like $3 or $4 each. But so you're trying to take the old spark plug out. You got the wrench there, and you're pushing on it, and it doesn't go. So you push harder, and it doesn't go. So you really lean right into it, and all of a sudden it lets go, and your hand just swings right around, and you punch the alternator and knock all the skin off your knuckles. You would think by now I'd know enough to wear a glove. But anyhow, as long as everything remains at rest, you're dealing with static friction. Eventually, you push hard enough that you've gotten up to the equals rather than the less than. And when you push just slightly harder than that, the spark plug begins to turn. Okay, the surfaces that are rubbing in this case is the threads where the spark plug screws into the engine, you know, the head in the engine. We got a threaded hole and a threaded bottom on the spark plugs, and it's the threads on the spark plug sliding across the threads in the hole. Anyhow, once the spark plug begins to move, now you're dealing with kinetic friction, which is weaker. But you haven't had any time to change how hard you're pushing. So now you're pushing significantly harder than friction is pushing back the other way, which means now that you've got this unbalanced situation, your hand is going to rapidly accelerate, which is how you end up punching the alternator. The thing that I'm oversimplifying is that there would be some changes in the normal force also as you free up the spark plug, but rather than make the story unnecessarily cluttered, part of what ends up knocking the skin off your knuckles anyhow is the fact that kinetic friction is weaker than static friction. There is a short table of friction coefficients. This is your formula sheet that you get to look at in the middle of a quiz or an exam. And these have been experimentally measured for a few materials. You can find references with considerably longer tables if you look up something for, that's not listed here. It's not going to happen in this course. So if you get some problem like in a homework or on a test or something that says you've got a steel block sliding across a steel surface, you go into that table and you look up steel on steel. One other point that I should make about the coefficient of friction over here. Coefficient of friction is an example of what's called a dimensionless number. Kinetic or static, either one. That's why I'm not putting the subscript on there. Mu, the symbol here, by the way, if I didn't mention that before, that is the Greek letter mu, which is the Greek version of the letter M. It does kind of resemble a regular m, which is more than you can say for some Greek letters. Mu is dimensionless, which is to say it is a pure number with no unit on it. If I take f equals mu n and I rearrange it, it becomes mu equals f over n. Well, for example, let's say that in one particular situation, the friction force was 4 newtons and the normal force was 16 newtons. Notice, newtons over newtons drops out. It's just a dimensionless ratio. There is no unit, just 0.25. A dimensionless quantity is something that takes on the same value in any system of units. Kind of rounding off and being approximate, 4 newtons is about a pound. 16 newtons, kind of sort of roughly 4 pounds, okay? Whether it's 1 pound divided by 4 pounds or whether it's 4 newtons divided by 16 newtons, it comes out 0.25. Because all it's telling you is that this force is 4 times bigger than that force. And it's going to be 4 times bigger no matter what you measure it in. Okay, so dimensionless ratio. You need to understand that if you're going to follow how the units work out in, when you start doing calculations. Okay, so where are we on the sheet over here? Fs is the force of static friction, which reaches a maximum when the surfaces are about to slip. The friction force is often less than this, like I wrote over there. The friction force is equal to the pushing force, or pulling force if you're pulling on it. Mu times n just gives you the upper limit on how big this force could be. And then sliding friction is always equal to mu k times n. Now, the reason this is called the normal force, normal is a word meaning perpendicular. Okay? I mean, why have just one word for something when 3 or 4 of them is 3 or 4 times as confusing? If you want to say 2 things make a 90-degree angle, you can call them perpendicular. Physicists kind of like the word normal. That's sort of a physics word. Mathematicians lean a little more towards saying orthogonal. But the reason it's called the normal force, okay, you've got something sitting on something else. The normal force points that way, perpendicular to the surface. If the thing is sitting on an incline, the normal force is still normal to the surface. The normal force is not necessarily vertical. If it was, we'd be calling it the vertical force and abbreviating it with a V. The normal force always acts normal to the surface, like this. If it's a level floor, then it's going to be vertical. But that's what's normal about the normal force. Basically, one way of looking at it, easier to draw a picture than hold that eraser on that box. There's the eraser sitting on the box. There is a force on that eraser, which is due to the fact that it's in contact with the box it's sitting on. It is usually convenient to take that contact force and essentially break it up into 2 components. The part of the contact force that's parallel to the surface it sits on, we call the friction force. And the part of the contact force that's normal to the surface it sits on, we call the normal force, okay? If it was a very slippery surface, like if there was little ball bearings all over it or something like that, then the friction force would be 0 and the normal force would be the whole thing. But in general, parallel is friction, perpendicular is normal. So that's why it's called the normal force. Said that. For the direction, all of this was about how to find the magnitude of the friction force. For the direction, friction always opposes motion. So, having said that, time for an example. And time to put another book under there so you can see the example. So it's the kind of thing I was just talking about, pushing an eraser across a box or across a table or something, except instead of pushing on it, I said there's a string attached to it and you're pulling on the string. Well, not a significant difference. So all the same forces that I was talking about in that sketch I already put on the blackboard a little while ago. It tells us that the box weighs 10 newtons, which means in this case, that means that the normal force is also 10 newtons. Now that's not always the case. Next example we'll get to, the normal force and the weight are not equal to each other. The normal force is a distinct thing from the weight. And yet another place where the red pen comes out is people assuming that they're always equal to each other. In this particular case, they happen to be equal to each other, but you shouldn't assume that because it's not always true. So anyhow, 10 newtons down, 10 newtons up. In part A, you're pulling the string with a 1 Newton force, and you're supposed to find the friction force. Now, the way to do this wrong, there always seems to be no shortage of people who would rather do things wrong by the look of the papers I get. So if you choose to do this wrong, the way to do it is to say, well, let's see, the block is at rest. So I'm dealing with static friction. Static friction is equal to mu s times n. So that would be 0.4 times 10. The friction force is 4 newtons. Let's think that through a little further. If you are pulling to the right with a force of 1 Newton, and friction is pulling to the left with a force of 4 newtons, friction is going to win. The block will crawl off toward the left, dragging you along behind it, and this is contrary to experience, okay? And the problem here is that mu s times n is simply the upper limit. That's the maximum that static friction could provide. There is nothing in part A that says you are at that upper limit. So the correct way to do part A is like, oh, I might as well just go over here and start a fresh spot. The question says, this box is at rest. Because it's at rest, the sum of the forces in the x direction is equal to 0. For that matter, the sum of the forces in the y direction is also 0, but it's the x direction that the friction force lies in, so that's what I'm interested in. So here's a little sketch. You're pushing that way with 1 Newton. Friction is the other way. And of course, there's also a couple of vertical forces. This is just a kind of a quick and sloppy sketch. But the point is, these are the x forces. And they have to balance. So one Newton to the right means there's also 1 Newton to the left in order for the thing to be able to sit there indefinitely. F is equal to mu s times n only when motion is impending. In other words, when it's right on the edge and about to slip, somebody breathes on it and it begins to slide. At that moment, that's when F is equal to mu s times n. If you're pulling with a smaller force than that, friction will oppose you with a smaller force than that. Part B says, find the push needed to start it moving. This is the question whose answer is 4 newtons. Well, technically, 4 newtons itself is the largest force friction can withstand. Any force greater than 4 newtons, like 4.001, except friction is kind of finicky. So you try it one time and you have to push with 4.1 to get it going, and then you try it the next time and it slips away at 3.9. That there is a reason that, is that focused? There's a reason that some of these are only given to 1 significant figure and the rest are only given to 2. Especially wood on wood, the first one on the list. You know, there's all different kinds of wood. Is it pine or is it oak? That's going to make a difference. Has it been sanded really smooth or is it kind of rough? That's going to make a difference. So these are just typical values, and you know, your results may vary. And even on the same board, if you try it in one spot, you're going to get a slightly different result than if you try it in a different spot. And so, yeah, somewhere around 4 newtons is where this is going to let go. Last part. How hard do you have to pull to keep it going at a constant velocity? A constant velocity being corresponding to the minimum amount you have to pull to keep it moving indefinitely. You could always pull harder and the thing would accelerate, but the minimum necessary for it to never stop would be if you just make a constant velocity. If the velocity is constant, then the sum of the forces equals 0, because in general, always and always, sum of the forces is equal to m times a. But if something has a constant velocity, its acceleration is 0. Acceleration means the rate the velocity is changing, and I just got done saying it's not changing. So this is a situation called dynamic equilibrium. Okay, I've already previously looked at objects at rest remaining at rest. That's called static equilibrium. The other half of Newton's first law, where an object in motion remains in motion along a straight line at a constant speed, that also involves no net force, okay? A net force causes acceleration. So since the forces have to balance, that means that the pulling force has to just balance the friction force. Pull harder and you'll make it accelerate. The coefficient of, I think I should write this down. Kinetic friction is mu k times n. Kinetic coefficient was given in the question. So you need around 4 newtons somewhere to get it started, but then once it's started, you only have to pull with 2.5 newtons to keep it going. If you keep pulling with 4, it'll accelerate. Okay, inclines. Well, like I was talking about back over, back over here. You got a box sliding down a ramp. So the only new thing to say, it's not something I've sort of already covered, is that it makes things a lot easier if when you do, because you have to handle all these vectors by doing components. When you do x and y components, you have to have x and y axes to do the components relative to. Your first impulse might be to say x and y mean horizontal and vertical. But on an incline, well, 99 times out of 100 anyhow, it's going to work out a lot better if you do the components parallel and perpendicular to the direction of motion, along and across the direction of motion, rather than horizontal and vertical. So let's put the camera back over here, and we'll run through the next example, which I think was on camera a moment ago. I probably shouldn't have moved the camera quite yet, but in case you didn't get it, it says example number 4, section 3, example 4, 5 kilogram wooden block is pulled at a constant speed up a 25-degree wooden incline by a rope that's parallel to the incline. Okay, this one's just a little practice doing the free body diagram. It doesn't ask us to actually, oh yeah, okay. I remember this one. This was an old test question, and I thought it would be a better thing to go over in class instead of having it on the test. Make a list naming each force along with how many newtons each one is. Right. So you always start with the diagram, unless you want to count erasing the blackboard. Then I guess the diagram would be step 2. So you've got this wooden board, and sitting on it, a 5 kilogram block. Maybe I should say right now, 5 kilograms is the mass of the block. You can tell because it's measured in kilograms. Kilograms a unit of mass. What are the forces? Well, a good place to start is with the weight, because that one's kind of a no-brainer. There is always the weight, unless you're floating around in intergalactic space somewhere. There's always going to be gravity. The weight, once again, is not 5 kilograms. Mass times 5 times 9.8. Weight equals mg, 49 newtons. other forces. It says, they call it a rope or a string. Okay. They called it a rope. I thought a nice name for the force from the rope might be R. For rope, parallel to the incline. Well, as you go dragging it uphill, the bottom of the box rubs against the, or it's not a box, it's a block, I guess. The bottom of the block rubs against the board, which creates a friction force, which actually acts down here on the bottom of the block, but it shows up better if I draw it over here, and it's all that matters is that it's pointing in the right direction. And as I was explaining earlier, the normal force acts normal to the surface. So, 4 forces. There they are. Next step is components. And the best way to do the components is along and across the direction of motion rather than horizontal and vertical, which means that instead of being horizontal, the x-axis goes like that. And instead of being vertical, the y-axis goes like that. And maybe you can kind of see already some of the advantages. If you tip the x and y axes like this, 3 out of the 4 forces are right on one axis or the other, which makes finding the components extremely straightforward. The only one where we're going to have both x and y components non-zero would be the weight. Because gravity is still vertical, okay, the force of gravity always points toward the center of the earth, no matter what. So gravity is vertical, and now the y-axis is not vertical. So gravity will have both x and y components. The question said, I didn't leave myself, I guess I can squeeze it. The question says that the board is tilted. It calls it a 25-degree wooden incline. That means 25 degrees out of being horizontal. This is a 25-degree angle down here. If that's 25 degrees, then this up here is 25 degrees. Well, I can explain that a couple of different ways. One is to say that since x and y have to keep the same, they have to stay perpendicular when you tilt them. So the amount that the x-axis has tilted out of being horizontal would have to be the same as the amount the y-axis has tilted out of being vertical. Or another way to look at it is to say if this is 25 degrees, then this angle up in here must be 90 minus 25. And since this is a 90-degree angle, if this is 90 minus 25, this one over there is 25. However you care to think of it, that angle up in the top of the triangle is equal to the angle of tilt. 49 newtons is the hypotenuse. Mistake I see sometimes people, there's the incline, there's that, there's the weight, and they go drawing. They just can't get away from this idea that the x-axis is horizontal. And I see them do the components like that. And yeah. So notice the x component is parallel to the x-axis. The hypotenuse is the 49. Adjacent side, 49 cosine. Adjacent side is cosine, opposite would be sine. So this is 44.4 newtons, and 49 sine of 25 degrees is it's 49 was the hypotenuse there. Okay, so draw the diagram, get all the components labeled, and then see, what did the question ask for? All of the forces. Okay, so it doesn't really matter what order you do it. We already know one of them. We figured out the weight already, 49 newtons. Let's go for the normal force next. That's in the y direction. Summation of the forces in the y direction equals 0. Because all motion is along the x-axis. It doesn't even move in the y direction, let alone accelerate. So in the y direction, things have to balance. Every place there's an arrow parallel to the y-axis, it's one of the terms in this summation. I've got that pointing up the y-axis. I've got the 44.4 pointing down the y-axis. So n is positive, 44.4 is negative. .4 newtons for the normal force. So as I was saying earlier, notice the normal force is a distinct thing from the weight. It weighs 49 newtons, but the normal force is only 44.4, okay, because it's sitting on a tilted surface. The normal force has to counterbalance not the full force of gravity, but just its normal component. Okay. Once you get the normal force, we can figure out the friction force. Since the block is sliding, that would be kinetic friction. Where does the 0.3 come from? Remember a few minutes ago, I was waving the formula sheet around, showing you how there's a table of friction coefficients. This question says that the block is wood and it's being dragged up a wooden incline. So you look up wood on wood. From the table, for wood on wood, mu k is 0.3. And we're just going to kind of sneak that in there. This comes out 13.3 newtons. So I've got everything except the rope force now. The force from the rope pulls up the x-axis. And actually I drew an X down there, but let's make uphill positive. Kind of moved where I wrote it. I put the X over there to kind of imply that was the positive x-axis, because you don't have to. You can do the problem either way, but quite often it's convenient if the direction of motion is what you're considering to be, or better yet, the direction that it's accelerating. But in this case, it's moving at a constant speed. But Well, anyhow, I did it that way. You don't have to. But if uphill is positive, then, well, first of all, the x forces also add up to 0 because it's a constant speed. Yeah, it's moving along the x-axis, but it's not gaining speed, it's not losing speed. So in m times a equals 0. In the positive direction, R for rope. Pulling downhill, maybe I should go back to my picture here for a moment. I'm calling this direction positive. So I've got the rope pulling uphill. I've got two different forces pulling downhill. I've got the friction force here, and I've got the x component of gravity, the 20.7, okay? So maybe I should put this back over here where you can see it better for just a moment. R uphill, 20.7 downhill, friction downhill, and I now know that friction is 13.3, okay? R minus 20.7 minus 13.3 equals 0. Maybe I should write this down. Something that makes perfect sense now, when you get your notes back out several weeks from now to review for the test, you might look at and go, what? So A equals 0 because A is equal to 0 because you have a constant speed. Okay, well, let's tie it all together. The question asked for a list. There are 4 forces. The weight, 49 newtons. The normal force, 44.4 newtons. The force of friction, 13.3 newtons, and from the rope, 34.0 newtons. So all of that is the, the question's got 4 answers. 4 things were asked for. Mistake I see once in a while is somebody will have all of that, and then they'll also throw in the 20.7 and the 44.4. Those are not distinct forces. They're not distinct from the weight. They are components of it rather than separate forces. I'm going to pause here for just a moment. Okay, one last sample problem, and that'll finish off section 3. This time, instead of a single object, we're dealing with a system of objects. I made one of them basically the same thing that was in the previous example. I just did that so I could be lazy and recycle some of the same numbers. But we've got a 5 kilogram wooden block on a wooden surface once again, but this time, instead of just being towed uphill by some force that we don't know where it comes from, there's some sort of a pulley at the top, like a frictionless wheel. The cord passes over that, and there's 10 kilograms hanging here. So part of it will resemble the problem I just did, but the pull of this rope will no longer be 34 newtons. It'll be something else this time. And in fact, finding how hard that rope pulls, the tension in the cord, that's one of the two things that the question asks for. So we're going to end up with two equations that have two unknowns. And we have to write an equation for each object, basically, is where the equations come from. You apply F equals ma to the block on the ramp, and you apply F equals ma to the one that's just hanging off the vertical cord. And between the two equations, you can solve for the two things that you're looking for. So here is where I wish I had a bigger blackboard, because I'd like to save some of those numbers. And well, you know what? If I just save the panel on the left, I can live without the one in the middle here. B301 used to have a lovely blackboard. It was a big. This one's 12 feet. The one in B301 used to be a 16-foot blackboard. I miss that. Anyhow, do it here. So isolate each object and apply Newton's second law. In other words, look at each object alone and apply the law to it. So we've got the block on the ramp. And a lot of the numbers are going to be there. If I just kind of slide that over a little bit so you can see where things are coming from. We've got the weight. And it's still 25 degrees. So the weight will have the same components it did before, which will be 44.4 on that side and 20.7 on that side. Of course, if the numbers had been different, you'd have had to repeat all of this, but like I said, I'm trying to save a couple of minutes. Actually, there's a couple of people outside the door waiting to get in here and do a lab, but they're early. But I should wrap this up. We've got R for rope, or T for tension, or whatever your favorite letter is for that. We determined that friction is 13.3 newtons. Okay, figured that out here. And we also know that the normal force is 44.4, but actually I'm not going to use that for anything, so I didn't bother to label it. And this is a 5 kilogram object. So summation of the forces in the x direction, where x means parallel to the ramp. Before it was sum of the forces in the x equals 0, because the block was keeping a constant speed. Now it's accelerating. or at least presumably it is, because the acceleration is one of the things the question asked for. So A is not 0 this time. Sum of the forces equals ma. So just like before, we've got the rope pulling uphill. We've got 13.3 pulling downhill, and we've got 20.7 pulling downhill. And that equals m times a. And I can combine those two numbers to simplify things a little bit. I've got r minus 34 equals one equation with two variables in it. Never going to solve that by itself. But we can get another constraint on the same two variables by looking at the other block. So maybe I can squeeze that in down here. There's the 10 kilograms over on the left-hand side of the picture. 10 kilograms would weigh 98 newtons. As for the upward force, it's the other end of the same rope that I had here. And to the extent that that wheel at the top of the ramp is a massless, frictionless pulley, which is usually a fairly decent approximation to reality, the tension in the rope will be the same all the way from one end to the other, okay? So the same number of newtons that pulls uphill on this block is going to be what pulls upward here. There is a trick. When I go to write my equation, the plus and minus signs are going to get you. If I haven't mentioned this before, minus signs are truly evil, okay? The snake in the Garden of Eden probably invented them along with the apple tree. There's always a minus sign just waiting to leap out and get you when you least expect it. Kind of like snakes lurking in the grass until you're practically on top of them. Anyhow, the trick is this. When I set up my first equation, I'm free to choose which direction is positive. Well, looks like I chose the direction that the rope pulls. So that's going to be the direction that this block is accelerating, okay? I mean, clearly you've got a 10 kilogram block trying to pull the one way. The other one's only a 5 kilogram block, and furthermore, it's only a component of its weight. It's pulling downhill. So the bigger dog is going to win. This block is going to go down, and this one's going to go up. So this thing is accelerating uphill. So when I wrote this equation, I built into it the assumption that the acceleration is a positive number. If I now write another equation for this, which has built into it the assumption that A is a negative number, now there is a contradiction. And when I put the two equations together, because they are inconsistent with each other, I will get garbage. So I was able to choose here. I was free to do it whichever way I wanted. But once I choose, I am committed. The acceleration has to be a positive number in this equation also, which means down is positive. And I want to write that down, but there's no space there, so I'm going to stick it over here. Down is positive in my second equation because you must be consistent. The direction of A is positive. So 98 newtons is in the positive direction. Incidentally, same acceleration. Because the two blocks are tied together, one of them can't start going faster than other without stretching out the rope or something. So same acceleration for both blocks. 98 is in the direction that I have chosen to call positive. R is in the negative direction. 10 times A. There is my second constraint on the same two variables. So, there's different ways of dealing with systems of equations. There's the addition method and the substitution method, and there's methods that involve determinants and well, this one looks like I used the addition method. So I've got looks like, I don't know, put that one on top, doesn't matter. 98 minus R equals 10A. Negative 34 plus R equals 5A. I mean, you could do it with the substitution method or some other way. You don't have to do it the way I'm doing it, but this is set up to, it's kind of set up to do it this way, because when you add them together, R minus R cancels out. You're going to have 98 minus 34 equals 64, plus 0 if you feel the need to write that down. 10A and 5A is 15A. So the acceleration is 64 divided by 15, which is 55.3 newtons. Notice, incidentally, that the force, I'm back over here. Notice that the force up does not equal the force down. Okay, that's only true when you're in equilibrium. An imbalance of forces is what makes something accelerate. The force down is more than the force pulling against that. That's why it's gaining speed. 98 down, only 55 up. What have I done? I looked away, and when I looked back, I looked at the wrong. Yeah, now that I made a mess out of everybody's notes, somebody's probably sitting out there going, 64 divided by 15 is not 55. Acceleration comes out 4.27. Sorry about that. Then, once you have the acceleration, you stick it back into either one of either one of these. Looks like I went with this one, but it doesn't really matter. So we've got 98 minus R equals 10 times 4.27. Oh, yeah, that's showing up all right. That's the 55.3. Might not be a bad idea when you turn the video off to see if you can do that yourself. If you can do this, you're in good shape, because a lot of what I've covered over the last couple of weeks is in here somewhere. If you can't do it yourself, watch me do it again, see if you can do it yourself then. But that's it for section 3. See you later.